Alright, in this video we are going to discuss the mean value theorem. The mean value theorem is very closely related to Rolle's theorem. In fact, Rolle's theorem is just a specific application of the mean value theorem. So we're just going to kind of generalize that a little bit more to get to this mean value theorem. So like Rolle's theorem, there are a couple of conditions that need to be met, and if those conditions are met, then the conclusion will be true. So first, the function just has to be continuous over the closed interval, and it has to be differentiable over the open interval from a to b. As long as those two things happen, then this is guaranteed to happen. And that is that there is a number c in AB, so there's some x value between a and b, where f prime of c is equal to f of b minus f of a over b minus a. So what does that mean? That means that the slope of the tangent line at c is going to be the same as the slope of the secant line between a and b. So if you look at this picture, hopefully this will make a little bit of sense out of that. That is my endpoints a and b. If I were to connect whatever my interval from a to b is, if I were to connect those 2 points with a line, whatever the slope of that line is, I can find some c value between a and b where the slope of the tangent line there is the same as the slope of the line connecting those 2 endpoints, which means those 2 lines will be parallel, right? So this line segment here and this tangent line, those 2 are parallel because the slopes are the same. So with Rolle's theorem, we had that third condition that a and b had to be the same. F of a and f of b had to be the same value, which means this line would always be a horizontal line. So in the mean value theorem, it's just saying that does not have to be a horizontal line, but I can find some c value in between there where I have a parallel tangent line to what that secant line is. Okay, so the setup's kind of the same. We need to state those 2 conditions to make sure that those things are met. So I first have to say that f is continuous on the closed interval from 0 to 2. And then I also need to say that f is differentiable on the open interval from 0 to 2. Okay. And again, I know both of those things because we are again dealing with a polynomial, so that's going to be the case when dealing with polynomials. That's all. Those are the only conditions that have to be met. And then we can say at this point in time that there's going to be this c value that exists. So I'm going to say so there exists a number c in the open interval from 0 to 2 such that f prime of c is equal to, now it's f of b minus f of a over b minus a, and I'm going to go ahead and use the values that we have here for b and a. So this is going to equal f of 2 minus f of 0 over 2 minus 0. So this is going to be kind of 2-part. First, I need to figure out what this slope is, right? So what is the slope of the line segment between 0 and 2? Well, f of 2, if I were to plug in 2 there, I would get 6. And f of 0 is 0. So this slope is going to be 6 minus 0 over 2 minus 0, right? F of 2 is 6 minus f of 0 is 0 over 2 minus 0. So this slope is 3. So what I'm going to do then is I'm going to take my derivative at c and set that equal to 3. Okay, so if I want to find what that value is, again, I'm going to do the derivative at c. So that's going to be 3c squared minus 1. Right? If I take the derivative and plug in c, 3c squared minus 1 has to equal, and then that right side we just figured out is 3. And then I can solve. So we would have 3c squared is equal to 4. So c squared is equal to 4/3. And so c is going to equal, now again, positive and negative, the square root of 4/3. But we are looking for a c value between 0 and 2, which means we want the positive square root. The square root of 4/3, which we could say would be 2 over root 3, so that's going to be 2 root 3 over 3. That is going to be our c value. Okay, so let's look at what that looks like in terms of the actual graph to help make sense of that. So I have the function graph, f of x equals x cubed minus x. Okay, we want to look specifically over the interval from 0 to 2. So if I make that show up, that's the blue part here. That is the part that we're looking at. So we could even maybe take this part away so that we don't see that, but that is the interval that I'm looking at from 0 to 2. We figured out that if we connect the endpoints, so 0 and 2, looking at those points, if I connect those 2 points with a line, that line has a slope of 3. Okay, so connecting the endpoints of my interval, the slope there is 3. We figured out that the value for c was the square root of 4/3, or 2 root 3 over 3. That's the value of c. I don't even know what that y-coordinate is. I just would plug in the square root of 4/3 into the function, but that is my value of c. And what we're saying here then is that the tangent line at c, if I make that up here, the tangent line at c is going to be parallel to this line segment between my 2 endpoints at A and B. And those 2 lines have the same slope. A little caveat here at the bottom: if f prime of x equals 0 for all x in the interval a to b, then f is a constant on a to b. So, if the derivative is always 0, that means the slope of every tangent line of every point in the interval from a to b is horizontal. If the slopes are 0, the tangent line is always horizontal, then the original function had to be a constant over that interval from a